So it's a pleasure to be here at Howard University, even though it's just a virtual visit. But I'm here to talk about my favorite mathematician, Leonhard Euler of Switzerland. This talk has three components. Let me just preview them. First, I'll do a bio, a short biography of Euler, giving you some dates and some chronology so you can place him in history. Second, I'm going to do a survey of just a few of his greatest hits, if you will, just talking about these, not in a technical fashion, but just sort of in an expository one, to give you some sense of the depth and breadth of this guy's genius. And then at the end, the third part, I'll actually do a proof. We will take a look at Euler's solution of the Basel Problem from 1734. And I'll put in all the details as he presented them. You can sort of join me in looking over his shoulder as he does a great theorem. So that's what's in store. Let's get going with the biography, and that requires that I show you a picture of Euler. And I'm going to show you a famous portrait. Done from life, and it's pretty clear that although he was a great mathematician, he wasn't so concerned with fashion, right? He was not a fashion icon. What a strange outfit. This is what he wore when he got his picture painted. Here come the dates. Let's see, let's see, I've just lost my, there we go. Okay. Born in Basel, Switzerland in 1707. By the age of 13, he was being mentored by Johann Bernoulli, and you might know that name, a great mathematician, great mathematical family. Johann Bernoulli happened to be in Basel, Switzerland, just by a fluke, when Euler was a young lad, and they arranged that Euler would meet with the great Bernoulli. So that's an interesting connection. He graduated from university in 1722 when he was 15, so he was moving fast. In 1727, he went off to Russia, to the St. Petersburg Academy. Now, in those days in Europe, the great courts would have these academies surrounding them. So in London, there was the Royal Society, there was the Paris Academy, there was the Berlin Academy, and Russia wanted one. So they were starting up the St. Petersburg Academy. And the idea was that this group of writers and musicians and scientists would enhance the reputation of the monarch and of the nation. So Russia wanted to be part of this, and Euler went off to St. Petersburg. He stayed there until 1741 when he went to the Berlin Academy in Prussia. Frederick the Great knew how great he was. He wanted Euler to come to his team, so he switched teams, and he's in the Berlin Academy, stays there until 1766 when he goes back to St. Petersburg, back to Russia. And while there, something kind of interesting happens. In 1782, Euler was made a foreign member of the American Academy of Arts and Sciences. Now, America, the United States, wasn't even started yet. I mean, the Treaty of Paris ended the revolution in 1783. So in a sense, there wasn't even a country here yet. But people like Jefferson and Franklin wanted an academy in the new world. And so they started the American Academy of Arts and Sciences, and they asked Euler if he would like to be a member. They sent him a letter, and he accepted. So in their archives, you have a letter from Euler, and he says, "Oh, thank you very much. I'm very honored to be a member, but I don't think I can come to your meetings," because he lived in Russia, and the meetings were in Philadelphia, so that wasn't going to work. And he was old, and in fact, he only lived one more year, died in 1783. So that's the bio, that's the sketch, and geographically, not much happened. Basel to St. Petersburg to Berlin to St. Petersburg. Mathematically is where things happen with Euler, not his actual travels around the world. He's buried in St. Petersburg. There's his tomb. And it might be interesting to connect him time-wise with people on this side of the ocean. So there's Euler in his characteristic outfit. He lived almost exactly the same lifespan as Benjamin Franklin. over here. And Franklin also wore strange clothes. He's got a dead animal around his neck there. If you look at that, but Franklin is a big shot here in my city of Philadelphia, but for your city, Benjamin Banneker lived almost exactly that same lifespan. So you get the sense that this is when we're talking about, not way back with Knights of the Round Table and not in the modern world with cell phones, but in the Enlightenment era, the 18th century. So that's Euler's period. He married, and he and wife Katerina had 13 children. But this was the 18th century, and childhood mortality was a horrible blight. And of those 13, only 5 survived to adolescence. So there would have been great sadness in the Euler household. He had, by all accounts, a phenomenal memory. He could memorize anything, poems, plays, tables, so he didn't have to look things up. And this became important when physical infirmity hits, because in the 1730s, Euler lost vision in his right eye. What we think happened was an infection got in, and not only cost him his vision, it actually destroyed the eye. So his eye shriveled. It was of no use. Nowadays, you take an antibiotic and you could fix this, but not then. So he has only one eye. So you figure, well, his productivity is going to fall. No, he kept going. That didn't stop him. In 1771, he lost vision in the other eye. And this was a cataract. And they tried surgery on him. And you don't even want to think about eye surgery in 1771. It was painful and it was a failure. So nowadays, cataracts are trivial, but not then. And in fact, he went blind. So now he can't see more than just vague images, apparently. So his productivity goes down, right? No, it doesn't. He keeps going. He would enter a room and start talking. He couldn't write on the board. He'd talk, and he had these people sitting there with their pens, their quill pens, writing, and then he'd send off a paper. It turned it into a publication. Or if somebody else had written something, Lagrange, D'Alembert, and Euler wanted to know about it, someone would read it to him and he'd listen. And then with this memory of his, he could sort of see it in his mind's eye, and he kept going. And if you don't believe me, in 1775, while blind, he wrote 50 papers. In that year, as a blind mathematician, he published a paper a week. And, that's just hard to fathom how you could do this. He's actually a great inspirational story in that regard, that he had this infirmity, but it did not stop him. And he's like Beethoven. If you know, Beethoven was deaf, and yet he could play, he would write music, and Euler was blind, but did mathematics. Now, both the quantity and the quality of Euler's work are breathtaking. I think that's fair to say. And let me just mention these. Let me mention the quantity of his work, because this is hard to fathom. Oops, let's see here. There we go. In 1783, Euler died. Over the next, 47 years, he published 159 papers. He's dead, but he's publishing papers. How does this happen? They were in his desk. They were in press. They were things they found in his notebooks. 159 publications. But he wasn't done, because he had a great year in 1844 while dead. He published 61 more papers that year. And then one more shot in 1849, 8 more. So as a dead mathematician, he published 227 papers, I think, if I added that right, which is never going to happen again. I promise you that. That's more papers than almost any living person could publish. In 1910, someone named Gustav Enneström decided to catalog all of Euler's published works, to collect them all and see what they were. And he wrote a description of each one. He found 866 books and papers, and that's really misleadingly low, that number, because a paper by Euler might be 100 pages. A book by Euler might be 1,000. So this was really a huge, huge amount of work. And when Enneström published the catalog describing all of these, the catalog was 388 pages long. That's not Euler's work. That's just a description of it. So this quantity is like off the charts, crazy. In 1911, the Swiss Academy of Sciences decided they would republish everything Euler published. It's called the Opera Omnia, and it's all of his collected works. And in 1911, a volume came out, and in 1912, a volume came out, and they're still coming. They haven't finished. It's over a century they've been working on publishing Euler's work, and they're not done yet. At the moment, there's over 70 volumes, 4 series, and 25,000 pages from one person. So nobody can even read that much, let alone write it that much. So the quantity of Euler's work is unbelievable. See, it sounds like fiction. But what about the quality? I mean, if it was just quantity, we probably wouldn't be talking about it. Here he did so many great things. And let me just share a few of these. In 1748, in his great work, the Introductio in Analysum Infinitorum, Euler stressed that the proper focus of mathematics, of analytic geometry, of trig, and of calculus was not the curve. Previous mathematicians had studied curves, sort of geometrical ideas. He said, that's not it. The focus should be on the function. And so when you go to class and you study functions nowadays in your pre-calculus course, why? Well, it's because Euler said that's how to do it, do functions. And it was up to him then to reveal the functions of note. And so he said, here's what you got to know. You got to know the polynomial functions, the log functions, the exponentials, the trig, the inverse trig functions. Those should be in the toolkit of all math students. And what do we have today in our toolkit?
Write your name on your TED speech.
We have exactly those same functions. So, this whole notion of function as at the core of analysis is from Euler. What else? Well, he gave us the number E. That's pretty important. And here's where it showed up. This is where E was born in 1748. Euler's writing. Of course, he's writing in Latin, as they did in the day. And if you look there in the middle, he said, we will place for the sake of brevity, this letter E to stand for the number 2.7182818284559. He loved carrying things out to lots of places. And so he's going to, rather than write that in decimal each time, he's going to call it E. And then just below that, it says, which therefore denotes the base of the natural or hyperbolic logarithm. So he knew what it was. That's E. And if you want to calculate it, down at the bottom, he shows you how to do it. 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3. That's the Taylor series for e to the x, where x is 1. It converges very fast, and that's how you do it. And so he's enshrined this number as being one of the real important numbers, and there it is. That's important. Same year, he gives us Euler's identity. Now, depending on where you are in your math training at Howard, you may or may not know this one, but this is it. E to the ix equals cosine x plus I sine x. This is called the Euler identity. Very strange formula the first time you see it, linking exponentials and trig functions, real and complex numbers. This is how he published it. This is from his work. That's what it looked like when it was born. Notice he wasn't using I yet. He has a square root of -1 in those spots. But he was doing COS and SIN, the abbreviations of the trig functions, although he put periods after COS and SIN because they were abbreviations. So he thought we needed a period there. We don't do the period anymore. When anybody shows you Euler's identity, they have to do what I'm about to do. It's in the contract. You got to show how this generates a famous equation. So there's Euler's identity, e to the ix equals cosine x plus I sine x, and mathematicians then always let x equal pi. So you put that in there, you get e to the I pi equals cosine pi plus I sine pi. And cosine pi is, of course, -1, and sine of pi is 0, and so you get -1. So e to the I pi equals -1, or if you bring the -1 over, you get this. E to the I pi plus 1 equals 0, a consequence of Euler's identity. Now, I mention this because in survey after survey, this wins as the most beautiful formula in all of mathematics. This is like the greatest formula of all, according to lots of people. Why? Well, it has in it the 5 great constants, 0, 1, e, I, and pi. They're like the dream team of constants. And there they are in this one equation. And it's just amazing, right? I mean, it's amazing that there is such an equation. Why should EI pi 0 and 1 have any connection at all? And then it's amazing that it comes so easily out of Euler's identity. So this wins the Super Bowl of formulas, so much so that someone wrote a poem about it. And I'm going to inflict this poem upon you right now. So here is the poem. E to the I pi plus 1 equals 0 made the mathematician Euler a hero. From real to complex, with our brains in great flex, he led us with zest, but no fear. Oh, so there. That's not Shakespeare, but that's the best I could do. So there's that. What else? Well, number theory. Euler was one of the great number theorists of all time. Of that opera omnia, that collected works of the 77 volumes or whatever, four of the volumes are number theory. Maybe 4,000 or 5,000 pages of number theory he wrote. And he did all kinds of important stuff. I'm just going to share one of the things he did. It's not the most important thing he did, but I find this kind of incredible. It requires a definition. Maybe you've seen this, I don't know, but we're in number theory now. Whole numbers, we're just dealing with whole numbers. Two numbers m and n are said to be amicable, which means friendly, right? They're friends, if each is the sum of the proper whole number divisors of the other. So that's a definition of amicable numbers. Now, an example is necessary, and here it comes. 220 and 284, I say, are amicable. Why? Well, what I have to do is look at the proper divisors of 220 first. Now, what I mean by that is whole numbers, they divide evenly into 220. And when I say proper, that means they're not 220, they're smaller. So what are the numbers smaller than 220 that divide into 220? There they are, 1, 2, 4, 5, 10, 11, 20, 22, 44, 55, and 110. Add those up, the sum of those proper divisors is 284. Now, look at the proper divisors of 284, all the whole numbers that divide into 284 but aren't 284. And there they are, 1, 2, 4, 71, and 142. Add them up and you get 220. Each of these numbers is the sum of the proper divisors of the other. It's a weird reciprocity, right? It's very strange. It's completely useless. I mean, if you're looking for applications, this will not make your refrigerator run any faster or anything like that. It's just what number theorists like. They like this kind of numerical magic. So this is what amicable numbers are. Now, I will share this little fact for you, with you. I had a friend, this is true, who on Valentine's Day, and Valentine's Day is coming, he got his girlfriend a bracelet with the number 284 on it, and he got himself a bracelet with the number 220 on it, and they wear these bracelets as a sign of their friendship, their endearing friendship. So I pass this on as an example if anyone's looking for a Valentine's gift. It is nerdy beyond belief, I know, but it's true. That's a true story. Okay. Now, here comes the history of amicable numbers. The Greeks knew that pair. They had stumbled upon 220 and 284. We don't know how, but way back, BC era, that pair was known. And so they thought, let's find some more of these. But they couldn't. That was all. They knew that one pair. Nobody finds any more until the 9th century, when the Islamic mathematician Tabit ibn Qurra finds a rule that generates 2 more pairs. So now there would be 3 pairs known. The Greek pair and Tabit had 2 pairs. But as far as I can tell, nobody in Europe knew about Tabit's work. It was lost or it wasn't translated. So back in as Renaissance Europe and the Enlightenment Europe comes along, they thought there was just the one pair. Okay, in 1636, the great French mathematician Fermat finds another pair, and there it is, 17,296, 18,416. If you take all the proper divisors of 17,296 and add them up, you get 18,416 and vice versa. And you can try this at home if you want, but this works. And Fermat was very proud of this. He did it. Well, that's one of Tabit's numbers. Fermat didn't know it, but he was just rediscovering what Tabit had done centuries before. Now, in 17th century France, there was a great mathematical rivalry between Fermat and Descartes. They hated each other, right? And Fermat just found a pair. So now Descartes has to find a pair to prove that he's just as good. And so he goes to work on this problem. And 2 years later, Descartes finds those two, 9,363,584 and 9,437,056. So there, Fermat, that was in your face Fermat or something. So Descartes proved his worth. Guess what? That's the other one of Tabit's numbers. Fermat and Descartes had just rediscovered what this Islamic mathematician had known centuries before. So the world supply was 3, but that was it. By the way, it seems to me if you really wanted to give your Valentine a special bracelet, you'd put 9,363,584 on one and 9 million, then boy, that would be profound. Okay, anyway, that's all people could find. And for the next century, that's all people could find. Nobody could come up with any more. And then along comes Euler. And he hears about this problem. And he thinks about this problem. And in 1750, he publishes this paper. It's called De Numeris Amicabilibus, on amicable numbers. And I put this up here to show you what papers look like in those days, but also because it lets me say amicabilibus, which I think is one of the great words. It brings a smile to my face whenever I say that. But anyway, in his paper in 1750, Euler, who had prior to this, remember, the whole world had found 3 pairs. Euler finds 58 more pairs all by himself. Pow! The world's supply goes from 3 to 61 in one paper. How did he do this? Well, he saw something. He saw a pattern that no one had seen, and it allowed him to generate these things willy-nilly. And, there's nothing you can say about that. It just blew the problem out of the water. It's so extraordinary that I will say amicabilibus, and what a guy. Okay. So number theory. Let me give you 2 more things he did, and then we'll get to my proof. You also have seen this sort of thing, right? The little circles. This is a Venn diagram, right? Wrong. Venn lived in the 19th century. This diagram I took out of Euler's work in the 18th century, 100 years earlier. So this should not be called a Venn diagram. This should be called an Euler diagram if we were to give justice to Euler, who understood the visual appeal of these little circles. Trouble is, if you do that, no one will ever remember who Venn is. This was, what else did Venn do? That's his claim to fame. Whereas Euler has lots of stuff. So we'll still call them Venn diagrams, but he beat Venn to the punch, and he beat lots of people to the punch. You can find Fourier series in Euler. You can find Bessel functions in Euler, and these people they're named after came decades later. And then one more thing, I'm going to call this a morsel. Here was a challenge given to Euler. Find 4 whole numbers, the sum of any 2 of which is a perfect square. So 4 whole numbers, add any 2 up, and you get a square, like, 25 or something like that. Well, as stated, that's trivial. I will give you 4 whole numbers that work: 8, 8, 8, and 8. And if you add any 2 of them, you get 16, and that's a perfect square. But that's too easy. So that wasn't the problem. This was the problem. Find 4 different whole numbers, the sum of any 2 of which is a perfect square. And now you've got yourself a real challenge. If you were to just try to guess your way through this, here it would go something like this. You'd say, I'll start with 1. All right. Now I need a number to add to 1 to get a perfect square. So how about 3? 1 and 3 is 4. That's a perfect square. Then I need a number to add to 3 to get a perfect square. So how about 6? 3 and 6 is 9. That's a perfect square. But you can see what happens. The 1 and the 3 don't work now. So then you have to go back and erase the 1 and turn it into a 10 maybe. So 10 and 6 is 16, but then the 10 and the 3 don't work. So if you just try to do this, it's like you're trying to juggle too many things and it won't work, and it'll wither on the vine. I promise you. You won't be able to just trip your way through this problem. You have to think about it. So Euler thought about it. And he said, how about these four? 18,530, 38,114, 45,986, and 65,570. And those work. You add any two of those together, you get a perfect square. He did this by having a method, of course, by seeing deeper into the problem than anybody had. And these fell right out. He was blind when he did this. And he did this without calculators or computers, of course, or anything of the sort. So, you look at this and you say, how does something like this happen? How can somebody in the 18th century come up with these numbers? Is this proof that he was a space alien or something? But no, he wasn't. He just was very, very smart and he had ideas. And there's my animation. I'm going to show it to you again because it's my only animation. There you go. He's Euler having an idea. So I hope I've suggested to you this guy was amazing. But now let me show you something mathematical, and that's called the Basel Problem. The problem came from Jakob Bernoulli. Remember, Johann Bernoulli had been Euler's mentor when he was a kid. This is Johann's brother, Jakob. And in 1689, in Basel, Switzerland, Jakob asked people to figure out the exact value of this infinite series. 1 plus a fourth plus a ninth plus a 16th. The sum of the reciprocals of the square. What is it? And that was the challenge. And because Jakob was writing from Basel, this became known as the Basel Problem. So this was what people were supposed to attack. Jakob couldn't do it. But he could do this. Let me show you what Jakob Bernoulli could do. This was kind of impressive, but it wasn't the solution. I'm going to get a bound on this sum. So here's an infinite series. We're going to find an upper bound, as Bernoulli did. He says, instead of writing it as 1 plus a fourth plus a ninth, I'm going to write it as 1 plus 1 over 2 times 2 plus 1 over 3 times 3 plus 1 over 4 times 4. There's the squares. And I'm going to compare that series with the one just below it. Leave the 1 in place in the front, but then instead of 1 over 2 times 2, try 1 over 1 times 2. Instead of 1 over 3 times 3, try 1 over 2 times 3 and 1 over 3 times 4. So there's two series. And you notice in each case, the number above is less than the number right below it. A fourth is less than a half. A ninth is less than a sixth. We made the denominators smaller, so we make the fractions bigger. So the upper series is less than the lower series. So I'm going to put a less than here. So then Bernoulli says, multiply these out, you get 1 plus a half plus a 6 plus a 12 plus a 20th. So his series, the one at the top, can't be any bigger than this one, 1 plus a half plus a 6 plus a 12. So let me move that to the screen. There we are. So we got a bound, but of course this doesn't help if I don't know what this series is, this second one. So here's what Bernoulli did. He said, I'm going to rewrite these fractions. Leave the 1 in front, but then you see the half, write that as parentheses 1 minus a half, which is a half. You see the sixth, that's a half minus a third. That's a sixth. Yeah. A 12th is a third minus a fourth. A 20th is a fourth minus a fifth. So the series that he's cranked out here is the same as the one just above, but now the minus 1/2 and the plus 1/2 cancel. The minus a third and the plus 1/3 cancel. The minus a fourth, everything cancels out the chain, except for the 2 ones at the beginning. And so his series added up to 2, and the Basel series is less than. And so what he had shown was that 1 plus a fourth plus a ninth plus a 16th is something less than 2. Now, this is an early example of the comparison test. You study this in calculus for infinite series, but this is one of the first uses of it. Very nicely done. And it showed, we would say, that this series converges to something below 2. That wasn't the terminology at the time. But okay, so that was good. But then Bernoulli didn't want to just say it's less than 2. He wanted to know exactly what it is, and he couldn't figure it out. And so he writes in his paper, if anyone finds and communicates to us that which thus far has eluded our efforts, great will be our gratitude. Please, can somebody figure out the exact value? And that was in 1689, and nobody could in 1699 or 1709 or 1719 or 1729. It was an open question. Anybody in Europe was working on it. Nobody in Europe could do it. Leibniz couldn't do it. Newton, nobody could do this. Okay, so then in the 1730s, along comes this young guy, Euler, and he finds a clever way to approximate the sum. And it's somewhere around 1.644934, he says, but that wasn't the exact answer either. And he said, Euler said, it seemed most unlikely to be able to find anything new about this. He was about to give up. But then, in 1734, against all expectations, he says, I have found an elegant expression for the sum of this series. He tells us he solved it. And so let me show you what he did in order to exactly figure out the sum of that series. It required 3 lemmas or preliminaries, I would say, 2 of which are very famous. One of them is he had to know when the sine of x is 0. Well, there's the sine function. We know that 0 at the integer multiples of pi, 0 plus or minus pi plus or minus 2 pi. So that was one piece of the puzzle. Okay, that was easy. Second thing he needed to know was what we would call the Taylor expansion for the sine of x. How to write the sine as a power series. Sine of x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. He knew that. Actually, Newton had discovered this a couple generations earlier. So this was well known. And if you've taken calc, probably calc 2 or something, you probably run across this. So that was the second piece. The third prerequisite is a little less well known. It was more designed for the problem at hand. So let me build up to it. Suppose I give you a quadratic, second degree polynomial, p of x, and I tell you 2 things about it. P of 0 is 1. So that's the y-intercept. It crosses at 1. And p of x equals 0 has 2 solutions, a and b. Okay. And let's assume they're non-zero solutions, a and b. So then I claim you can factor this quadratic, p of x, like that. 1 minus x over a times 1 minus x over b. Now, if you think about it a minute, let's just make sure we believe this. Certainly that is a quadratic because there's 2 binomials with x's in them. If you multiply that together, you get an x squared term, so it's second degree. Notice if you put 0 into that, p of 0, you get 1 minus 0 over a times 1 minus 0 over b, which is 1, as it's supposed to be, according to a up there. And if you put little a in there, p of a is 1 minus a over a times 1 minus a over b, but a over a is 1, so you get 1 minus 1 times something, which is 0. And if you put b in there, you get 0 because 1 minus b over b is 0. So this works for factoring second degree with these conditions. Okay, now Euler says, well, let's say we had a third degree, a cubic. And suppose p of 0 is 1, as before. And now when you set p of x equals 0, you get not 2, but 3 solutions, a, b, and c. How do you factor it? He says it's going to factor like this. 1 minus x over a times 1 minus x over b, and then there'd be another term, 1 minus x over c. Check it. It's cubic. Yep. P of 0 is 1. Yep. P of a is 0. P of b is 0. P of c. Yeah. So that works. Now, Euler says, let's extend this not from the second degree to the third degree to the fourth degree. Let's go to the infinite degree. And Euler would do this. Back in those days, if something was true for finite cases, you just extend it to infinite cases. We now know that's a little dangerous, but this is how they did it. So he's going to look at an infinite degree polynomial. I mean, there isn't even such a thing, but like a power series. Think of that. And suppose p of 0 is 1. And when you said p of x equals 0, now you get infinitely many solutions, a, b, c, and c. How do you factor this? He says the same way. The same pattern will hold. P of x will be 1 minus x over a times 1 minus x over b times 1 minus x over c, dot, dot, dot. Every solution, every a, b, c, d, e gives another factor, 1 minus x over that. And so he's happy to go with this as a kind of extension of his factorization from second degree to third degree to infinite degree. And with those three little preliminaries, he's ready to solve the Basel problem. All right, now, I don't know if somebody gave me those three preliminaries, I still don't think I know what to do, but here's what he did. He says, if I want to evaluate 1 plus a fourth plus a ninth plus a 16th, I'm going to start with this infinite degree polynomial. Here's the critical one. P of x is 1 minus x squared over 3 factorial plus x to the fourth over 5 factorial minus x to the sixth over 7 factorial, and so on. It goes on forever. Infinite degree polynomial. He wants to use his factorization scheme. So he has to, first of all, check what's P of 0. It better be 1. Well, yeah, if you put x equals 0 in there, every term is 0 except the 1 in the front. So P of 0 is 1. So that's good. Then he needs the solutions to P of x equals 0. Because those are going to be like the A's and the B's and the C's when he factors this thing. Well, that looks like trouble. How in the world are you going to solve that? P of x is an infinite degree creature, 1 minus x squared over 3 factorial. I want to solve that. He said he can do it. Here's what he does. He sets 0 equal to that, 1 minus x squared over 3 factorial plus x to the fourth over 5 factorial, etc. He's trying to solve it. Draw a line and turn it into a fraction. On top, hit it with an x. On the bottom, hit it with an x. Okay, so it's still equal, right? You could take away the x's, it's still the same. So you just put these x's in here. All right, now what? 0 equals, so there's your fraction. There's an x on the bottom. On the top, he distributes the x across, multiplies. So now he gets x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. Every power goes up 1 when you hit it with the x. And he recognizes that numerator. That's the sum. That's the Taylor series for sine. So when he's trying to solve P of x equals 0, he's down to trying to solve sine of x over x is 0. But that, if you just cross multiply, amounts to solving sine of x equals 0. And we saw in that first preliminary, when is the sine of x 0? 0 plus or minus pi plus or minus 2 pi. Those are the solutions to P of x equals 0, with one caveat, one exception. Remember, P of 0 was 1. We checked that, not 0. So P of 0 isn't 0, and we have to throw away that 0. That's an extraneous root. And you can even see where it came from. I divided everything, I multiplied and divided everything by x. Well, when you do that, you cannot have the x be 0. And so 0 isn't even in the conversation here. And in fact, 0 is not a solution to P of x equals 0 because P of 0 is 1. But the other terms are pi minus pi, 2 pi minus 2 pi. Those are the roots. Now, remember what his principle was. If he knew he had an infinite degree polynomial P of x, he knew that P of 0 is 1, as it is here. He knew the solutions A, B, C, D. Then he would factor it into 1 minus x over A, 1 minus x over B, and so on. So now he's ready to factor P of x, because these things, the pi and the minus pi and the 2 pi and the minus 2 pi, those are like the A's and the B's and the C's. So here's his setup, and now factor. So he says P of x can be factored as follows. So first I've written P of x, what it was originally given as, this series, 1 minus x squared over 3 factorial. One of the factors will be 1 minus x over pi, because pi was one of the solutions. One will be 1 minus x over minus pi, because that was a solution. 1 minus x over 2 pi, 1 minus x over minus 2 pi, 1 minus x over 3 pi, 1 minus x over minus 3 pi. There's an infinitude of factors, of terms here. Now, what I'll do next is clean this up a little bit. Instead of having 1 minus x over minus pi, let's just write that second one as 1 plus x over pi. Then you got a 1 minus x over 2 pi, and then you got a 1 plus x over 2 pi, and a 1 minus x over 3 pi. So he's factored it in his 18th century fashion. I don't see the solution to the Basel problem yet, but he's getting there. So let me write that up there. There's where we are. P of x originally given as this infinite series, and now in the line below, it's an infinite product. So you see what he's done. He's written the same thing. P of x is a sum and as a product, but it's the same thing. And by matching and comparing these two different versions of P of x, he's going to get somewhere. All right, here's what he does next. you're going to take these terms in the product pairwise. Look at the first two, 1 minus x over pi, 1 plus x over pi. If you multiply those together, it's like a difference of squares. You get 1 minus x squared over pi squared. The next two, 1 minus x over 2 pi, 1 plus x over 2 pi is 1 minus x squared over 4 pi squared. The next two, 1 minus x squared over 9 pi squared, and so on. So that's the product version of P of x. So let me put that back up here. Now I'm beginning to see something, look down there in the bottom. I see a 1, a 4, a 9, a 16. And remember that the Basel problem was trying to add up those reciprocals. So you start to get the idea he knows what he's doing here, but he's not done yet. Now what he says is take that product at the bottom and multiply it back together. Multiply it out. All right, so let's think about this. If I were to multiply all those terms, there's an infinitude of them, but I'm going to multiply them. What's the constant that will emerge here? Well, you get a 1 from the first square bracket times a 1 from the second times a 1 from the third. So you get a 1 times 1 times 1. I don't care how many times you multiply it, you get 1. How many x to the firsts are you going to get if you multiply this out? X to the first power? None. You can't get an x to the first out of this. All the powers are even. So there's not going to be any x's. How many x squared are you going to get? Well, he says, look, where are you going to get an x squared? You see in that first square bracket, there's minus 1 over pi squared x squared. Suppose that hits all the other ones. That'll give a minus 1 over pi squared x squared. In the second square bracket, you have a minus x squared over 4 pi squared. Suppose that hits all the other ones. You get a minus 1 over 4 pi squared x squared. The third term will give you a minus 1 over 9 pi squared x squared. So if you collect those all together, that's going to be the coefficient of the x squared. What's the coefficient of x cubed? Can't be. No x cubes could possibly come out of this. How about x to the fourth? Well, I don't care. We don't need it. So I'm going to just say stuff happens. Actually, Euler figured it out. He knew what the coefficient of x to the fourth was also, but we don't need that. So I'm using a technical term here, stuff. And that's what follows. And now, here's where we are. The P of x given as a series initially, then factored and then remultiplied gives me a series again. Notice they both start with 1, and then there's no x terms, and then you come to the x squares terms. And what Euler says is equate the coefficients of x squared in the two versions of P of x. In the top one, the coefficient of x squared is minus 1 over 3 factorial. You see it up there. In the bottom one, the coefficient of x squared is that thing in the square brackets. Minus 1 over pi squared, minus 1 over 4 pi squared, minus 1 over 9 pi squared, forever and ever. Now, change all the signs to plus and factor out a pi squared on the right. And 3 factorial, 3 times 2 times 1 is 6. You get 1 over pi squared times square bracket, 1 plus a fourth plus a ninth plus a 16th, the very series that Bernoulli wanted people to sum. And so from that, it follows by cross-multiplying that 1 plus a fourth plus a ninth plus a 16th is pi squared over 6. And that's the answer. And that was the solution. Euler had solved the Basel problem in that fashion in 1734. He publishes this and becomes famous around the world. This was his first great result. And after that, everybody knew that there was this guy in St. Petersburg that you had to take seriously because he solved the problem that generations of mathematicians couldn't. And he did it like that. Now, if you understood that and you got in a time machine and went back to 1720, you could have solved the Basel problem. It wasn't that hard in some senses. But on the other hand, it was extraordinarily ingenious, brilliant. How in the world did he think of this? Notice, amicabilis. Yes, it's time for me to say amicabilis because, hey, that was pretty great. Okay, notice that if you get out your calculator and look at that value, pi squared over 6, it is less than 2, as Bernoulli had shown. So Bernoulli was on target. And it also is about equal to 1.644934, as Euler had shown. So they were both, zooming in on it. But neither of those results was what we were after. We were after the exact value. And remember, Euler said, against all expectation, I have found an elegant expression for the sum of this series, that 1 plus a fourth plus a ninth plus a 16th is pi squared over 6. It's one of the great formulas in the history of mathematics, one of the great stories. Now, in the subsequent centuries, this became part of a much broader topic of the zeta function. Some people might recognize this as zeta of 2. This is just how that all was getting started in the century before, but it was a brilliant deduction. The math historian Ivor Grattan Guinness said of Euler this. He said, Euler was the high priest of sum worship, for he was cleverer than anyone else at inventing unorthodox methods of summation. And what I've just shown you, it seems to me, is an unorthodox method of summation, but incredibly clever. So this is why I like him. And this is why I'm going to end this with a shout out. Way to go, Uncle Leonhard. Thank you.
Thank you very much for the very, very interesting talk and enlightening. So are there any questions?
Can I ask a question?
Sure.
Yes.
Okay, I can't find my, I was just curious about, did he try zeta of 4?
Yes, he did it. Not initially. Initially, he just did the zeta of 2. But later he got zeta of 4 was pi to the 4th over 90, and he got zeta of 6, zeta of 8, 10, 12, all the way up to zeta of 26. He went up and actually calculated that, which is unbelievable, incredibly complicated expression. So yes, he was on top of that. He had a more general technique. He did revisit this problem. I'm trying to get the screen so I can see everybody here. He did revisit the problem later and got other techniques for getting the sum, but this was his first.
Okay, thank you.
Thank you, Francois, for your question. Any other questions?
So did he know that that it had to do with the sort of, that it was related to a series of cotangent, basically the coefficients in it?
Yes, he does that too. Yeah, that was later. I'm thinking that might have been maybe in the 1740s. He comes back to that and gets the cotangent series, and which is incredible, right? Another one of these amazing formulas he cranks out, and he used that to sum the Basel series. That was a second way. He did it with infinitesimals. Back in those days, they believed in infinitely small quantities. A quantity that was not 0, but it was infinitely small. And so he would take the series for sines and cosines and substitute in dx for the variable. So infinitely small things, and it throws some of these away and keeps some. And if you do that right, you get pi squared over 6 is the sum of the series also. He had many different attacks. Maybe he had one with integral calculus. He actually has an integral that comes out to be this series, and he evaluates the integral. It's just amazing how fluid, how agile he was. But this was the original, so this was the classic.
Thank you very much for that talk. That was a lot of fun.
Oh, you're welcome. Euler's pretty amazing.
Yes, he is.